Hi, my name is Konar-Steenberg, and for this year's Science and Engineering Fair, I'd like to introduce to you my game. It's tentatively called the Raft game, and it uses player objectives to construct an adaptive virtual gameplay environment. So what do I mean by that? Well, exploration is a very important part of the video game playing experience for a lot of players. Science has shown that kids, when given the opportunity to explore something, will do it even if there is no inherent external reward in doing so, and the same is true for players playing a video game. However, creating areas for a player to explore is an onerous task, even for experienced developers, because it takes a lot of time, a lot of energy, and a lot of money and resources. To that end, a lot of developers have decided to rely on random generation in order to create terrain for their players to explore. The video game Legend of Zelda Breath of the Wild, which was released in 2017, has received critical acclaim for its large and explorable open world. But creating that resulted in costs for the developer, Nintendo. And on the flip side of this, video games such as Minecraft use random generation in order to create a lot of terrain for a player to explore without needing to create that all by hand. So there are many different types of random generation methods. One of them is what's called Perlin noise scaling. The image you can see on the left side of this slide is Perlin noise. And if you'll imagine the dark areas to be like mountains or areas of high elevation, and the white areas to be valleys or low elevation, you can see how this random noise could correspond to terrain. There are other methods such as procedural generation, which generate terrain in ways that follow a predefined algorithm. This is used for structures like trees or buildings that a developer wants to create. And there are other ways developers randomly generate terrain as well. The thing all these methods have in common is that they all need to be appropriate for the developer's end goal. And random terrain can bore a player or make them feel as if what they're exploring just is irrelevant to their goals. For instance, if you're playing Minecraft and you need to get string in order to build a bow, it won't help if you can't find any places where a spider may spawn so that you can kill it and harvest its string. So how do we fix this? Well, my solution to this problem is adaptive terrain generation using weighted objective prioritization. That's a lot of words, but to put it simply, the terrain itself is random. And an algorithm ensures that it stays relevant to the player's goals, or in some other way it remains interesting. So to illustrate how this process works, I created the video game Raft game. You can see in the image that is a cat on a raft in the game. So the essence of the game is that you play as a cat drifting down an infinite river. If you bump into the coastline, your raft will lose durability. You can repair your raft with materials that you find on the land surrounding the river. But if you leave your raft for too long, it will float away. So there's an element of difficulty in being able to manage how long and how frequent your trips off the raft and onto the shoreline are. So how does random generation work in Raft game? Well, there are three elements of random generation that I have put into the game, which I will talk about in sequence. Firstly, generation of biomes that the player will go through. This is accomplished through something called random walk generation. Then there is generation of the coastlines of the river and the width of the river. This is accomplished through scaled, stacked Perlin noise functions. And then there's the generation of trees and plants and terrain on the side of the river. And this is done using procedural generation through noise. Each of these random generation functions, however, are modified to alter the difficulty of the game relative to a player's current objectives in trying to get farther down the river. and this ensures that a player's surroundings contain materials relevant to their current goals. So how does biome generation work in the game? Well, there's a what's called a temperature value, which scales from 0 to 1, and a higher temperature means more trees are able to grow in that biome. On each generation cycle, and by generation cycle I mean a point in the code where the code will generate a series of 30 blocks lengthwise, so the direction that the river is going, and 130 blocks wide. On each generation cycle, this temperature value is altered by a certain amount. It can increase or decrease by up to 0.2. This number is then subject to the formula that you can see on screen. And essentially what that does is it scales the temperature amount in order to ensure that whatever biome is around the player, if the difficulty is supposed to be hard, it will not contain resources that the player needs in order to progress. If the difficulty is supposed to be easy, it will contain those resources. This difficulty follows a sine curve you can see on the slide there. It talks about the function diff curve. That is a scaled sine wave that the difficulty of the game follows. The result of this is that the availability of trees on the shore in order to repair the raft goes up and down, and this is affected by how well the raft is doing. So how is the coastline of the river generated randomly in Raft game? Well, it's done through 3 stacked Perlin noise functions. There is the river function, and this is a 1 block wide series of water blocks. And a Perlin noise output dictates where, on the width of the land that is generated, where the river is. This is so that the river can take bends and turns. The left coastline and right coastline functions are then added to this water on either side. The coastlines are between 0 and 4 blocks wide of water, and this width is affected by what is called the coast width constant. And this is a number that scales depending on how repaired the player's raft is. If the raft is in bad shape and the difficulty is supposed to be high, the river will narrow, so there's more likelihood of the player running into the coast and losing their progress. So if one is off the raft for long enough, the raft will float away. But a player needs to leave the raft in order to obtain materials to repair the raft. So while a player is in a location with lots of trees in order to repair the raft, and they need to repair it so it's in bad shape, if the difficulty curve is at its absolute highest level, it won't take very long for the raft to float away. If it is at a low level, it'll take quite a while for the raft to float away. This is accomplished using a variable that counts down 1 every game loop. And the threshold for the point at which the raft will float away is a lot more stringent when the difficulty is high. So what are the end goals that I have for Raft game? Well, the goal of the random generation is to create an experience that ultimately adapts to the player's needs to ensure that they enjoy themselves in order to solve the major problem with randomly generated terrain, which is that it isn't relevant to what the player is trying to do. However, there are ways to improve upon this solution, and these are solutions that I would like to implement later into my project. One of them, which I've thought a lot about, is the use of neural networks. I have a lot of constants and numbers that I need to carefully balance in order to tailor a certain level of difficulty for a player. And neural networks are very good at managing these sort of constants and at adapting to a certain play style. I'd also like to do more investigation into how players actually end up playing this game, and where I could use more or less contemporary random generation methods. I'm trying to hit a good balance between prefabricated terrain and randomly generated terrain. So yeah, that's my project. Here are my works cited, and thank you for watching.